Okay guys, we are looking at how to solve limits analytically and the properties of limits. And on page 59 in the text, you should have all those properties already written down when you read that and took notes over that. I'm just going to talk about three of them and then show you some examples of how we can use those properties and solve limits analytically so we don't have to graph them and we don't have to make a table to find their limit. So the first thing is we want to look at this property. This is the major one. The limit as x approaches c of some other constant. I'm just going to call it b. That equals b. And so my example for that would be like the limit as x approaches 2 of 7. That equals 7. That's simple. The limit of a constant is a constant. That's all it's saying, no matter what x is approaching. Next one that we want to look at, the limit as x approaches c of x. Just plain old linear x. That equals c. And the reason that works is if you, let's say, have the limit as x approaches 2 of x, well, if you think of that line, as x gets closer to 2, your y value is 2. So f of 2 is 2. So on a linear like that, remember your f of 2 is going to equal the limit as x approaches 2 because a line is continuous and it works out perfectly. The last one I want to show you, and this kind of will lead us into some examples, the limit as x approaches c of x to the n, so some power. The limit as x approaches c of x to the n is going to be c to the n. For an example, let's look at the limit as x approaches 2 of x to the third. That's going to equal 2 to the third, or 8. And you got to remember when you're looking at these functions like this polynomial function, a cubic's going to be continuous, so that's why that works out nicely. So f of 2 in this case, or whatever value you're going to, is going to be the same as the limit as x approaches 2. Both these two functions that we have these properties for are continuous, so that's why that works out nicely. Most of your problems for today will work out nicely. Alright, so let's look at a couple examples, and like I said, make sure you look at the other properties that are on page 59. I'm going to be using them, but I'm not going to write them all down because you can do that on your own time. So let's look at this. The limit as x approaches 1 of 3x cubed minus 2x squared plus 4. Now, I'm going to rewrite this first one, but after this I'm not going to do all this because you're going to figure this out pretty quickly. I could rewrite this as different limits. The limit as x approaches 1 of, well, 3 is a constant, so I'm going to move it out front. 3x cubed minus 2 times the limit as x approaches 1 of x squared plus 4, the limit as x approaches 1 of 4. Well, this last one I just wrote, that's that first property. The limit of a constant is itself, so 4. This one, if I plug 1 in, this is this power one, the third property. 1 squared is 1 times 2 is 2. Here, this is a power property again. 1 cubed is 1. That's 3. 3 minus 2 plus 4 is 5. More simply, if I go back to this original problem right here, and this is continuous, I know this is continuous because it's cubic, this domain is all reals, I can just plug in 1. And I tell people that when I'm doing limits, the first thing I always try is just to plug in the number. So if I just plug in 1, I get 3 times 1 cubed minus 2 times 1 squared plus 4. That equals 5. Okay, so let's try, you can do that with pretty much anything. The limit as x approaches 6 of 5x squared plus 2 over x minus 1. Now this problem, we know that this function itself is not continuous because of the denominator, but I really don't have to worry about it because the only place it's not continuous is at 1, so I can still just plug 6 in. 5 times 6 squared plus 2 over 6 minus 1 equals some number. I'm not going to figure that out yet. It equals something, and you can figure that out. So if you can just plug the number in and you don't have a 0 in the denominator and everything works out, plug the number in. Alright, limits also work. Like if I have f of x equals x plus 7 and g of x equals, we'll say x squared, and let's say I want to find the limit as x approaches 2 of f of g of x. I can do that using my algebra. I'm going to plug g into f first, so that becomes the limit as x approaches 2 of x squared plus 7, which is continuous, right? There's nothing that's got discontinuity in the domain, so you get 11. Very easy. All right, you're going to be doing problems like that today, or for the next time I see you, I guess. A couple other things I want to tell you about limits. They work with trig functions. The limit as x approaches pi over 2 of the sine of x. And sine is continuous everywhere, so I don't even need to check that. I can just plug that in. So the sine of pi over 2 is 1. Some of your trig practice problems that you're going to do in class, you might have to remember like tangent, sine over cosine, and some of your identities. But they're pretty easy. You can plug them in and get them as long as they're continuous and you're not getting 0 in the denominator.